When you look at a scatter plot, your perception of the strength of a linear association between your variables is sometimes affected by the scaling of the graph, or is sometimes subject to your personal judgment about that strength. It would be nice to have a numerical measure of the strength of a linear association, and we have one in the correlation R. That's a numerical measure of the direction and strength of a linear association between two quantitative variables. Now here's the formula for it. It's quite nasty looking. R equals 1 over n minus 1, where n is the number of observations we have. And then we have this big sum right here. This means sum. What we do here is we take, for the first value in our data set, we take that x value and we subtract the mean of all the x's and divide by the standard deviation of all the x's. That right there forms a z-score for that first observation. Over here, we take that observation's y value and subtract the mean of all the y values and divide by the standard deviation of the y's. And this gives the z-score of the y value. Then we multiply the z-score for the x value and the y value for that observation together. And then we repeat the process for all the observations in the data set. We calculate an x z-score and a y z-score and multiply them together. And then we add them all up, all those products, and then we divide by n minus 1. So it's a fairly difficult or tedious process to do by hand. Fortunately, you have a calculator that can help you with this sort of thing. Now, these are some important things to know about this R. First of all, the expressions in the parentheses are the z-scores for the x values and the y values. Since these z-scores are unit-free, whatever unit you measure x in, you're going to subtract the mean, which is in the same unit, and divide by the standard deviation in the same unit, and the units cancel out. So since that z-score is unit-free and this z-score is also unit-free, R is unit-free. So whenever you're talking about this R, never attach a unit to it. It's a unit-free number. Okay, R is independent of the units in which x and y are measured. And if you were to change the way you measure x or change the units in which you measure y, that would have no effect on R. So not only is it unit-free, but it's independent of the units in which x and y are measured, and changing units of measurement for x and y has no effect on R. R is the same regardless of which variable we call x and which we call y. Up here, you're multiplying two quantities together. It doesn't matter which one comes first and which one comes second. So it doesn't matter which one is called x and which one is called y. It makes no difference. So the explanatory response distinction is irrelevant when you calculate R. Another thing you need to remember about R is that your x and y variables have to be quantitative. You can't calculate a z-score for a categorical variable. There's no such thing. There's no mean. There's no standard deviation. The z-score is just not possible to calculate in that situation. So remember, you cannot calculate a correlation for categorical variables. Okay? R applies only to linear relationships. It cannot be used to describe nonlinear relationships, no matter how strong they might be. Always make a scatter plot of your data before calculating R, and verify from the scatter plot that the relationship looks linear enough in order to make R a meaningful number. Now, R is some number between -1 and +1. If the relationship is positive for a positive linear association, R is going to also be positive. And for a negative linear association, R will be also negative. So the sign of R, whatever it is going to be the same as the direction of the linear association between your variables. The stronger the linear association, the closer R is going to be to 1 or -1. R will be equal to 1 or -1 only when the data points are perfectly collinear, which is rare. It could happen, but not with real-world data in general. So if R equals 1 or is close to 1, that indicates a very strong positive linear association. And if R is near -1, that indicates a very strong negative association, linear association between your variables. Now, R is not resistant to outliers or influential points. A couple reasons why. X bar and Y bar are not resistant. Sx and Sy are not resistant. So the means and standard deviations of your x's and y's are not resistant. And since you calculate R from those things, R will not be resistant. Now, in the previous video on scatter plots, we drew some pictures. This one is the first example from that video on listing price versus house size. And we have the data here. I calculated the correlation using my calculator rather than the formula, and I got that the correlation was equal to 0.8357 for the linear association between these two variables, listing price and house size. That indicates a moderately strong positive linear association between listing price and house size. And if you have to interpret a correlation, this is basically all you need to say. You say what the correlation value is, and then say what kind of strength that indicates and what kind of direction that indicates for a linear association between your two variables, and you put the two variable names in there so that you have some context. Here's the second example we looked at, games won versus runs allowed, and you can see that there's a negative linear association between our two variables, and the correlation came out to be negative 0.9218. That indicates a strong negative linear association between games won and runs allowed. Again, when you write a description of a correlation, put the number in and then indicate the strength and direction of the linear association between, and then specify what two variables you're talking about. Here's a third example we looked at, games won versus errors committed, and we saw that this was a very weak linear association between games won and errors committed, and the correlation worked out to be negative 0.2487. That indicates a weak negative linear association between games won and errors committed. Now, how do you calculate these things? Well, this can be done on your calculator. I'll put back the data from the first example right here. And what you do is, the first thing you want to do is make the scatter plot. So go in and put the data into your calculator. So you go to Stat Edit, and over here in List 1 and List 2, I have my square footage, my house sizes, and my listing prices for those 7 houses. And then if you want to make a scatter plot of these data, go to second y equals, up to Stat Plot, and then turn Plot 1 on. And then right here on the type line, this one is the scatter plot. So select that, and then specify where your x values and your y values are. Mine are in List 1 and List 2. And then you can choose what kind of mark you want to make for the points in your scatter plot. I usually use the square because it's easiest to see, but if I have a lot of data points, I'll use the dot. But in this case, I only have 7, so it's not going to take up that much space. And then I just go zoom 9, make the scatter plot. There it is. You can see that it's a moderately strong positive linear association between listing price and house size. So it's okay to go ahead and calculate a correlation. Now, the way you do that is you just go to Stat, and then you go to Calc, and you select number 8 on this list, which is linreg A plus BX. This actually does a linear regression, and you can specify what lists your X's and Y's are in, L1 and L2 in this case, and then you run the regression, and you can see the correlation down here, 0.8357 approximately, which is what we calculated before. Now, when you do this, sometimes your calculator will not show R squared and R. Okay, if you're not seeing those things, go to second of 0 into the catalog. See where it says second 0 right here? Above the 0 key, it says catalog. Go into that, and then you can scroll down to the D's, and you want to select diagnostic on. It's way down. There are shortcuts to get here, but you can see here, it's a long way down to diagnostic on. You select it, and then you see your cursor's blinking right there. You have to press enter again to execute that command. And then anytime you conduct a linear regression on your calculator, R squared and R will show up. Okay, so it's something I would leave, I would just set up your calculator to do that and then just leave it that way all the time. So that anytime you do a regression, you get a correlation. Anytime you want to calculate a correlation, you can do a regression and get it that way. Now, just to sum up, here are a few things to remember. Okay, you want to never use the word correlation unless you're talking about a linear relationship between two quantitative variables. Very important. In fact, I would never use the word correlation unless I was talking about R specifically. It's too risky to use the word correlation in general unless you're talking about R, because it's easy to slip into this trap that everybody falls into. Never, ever, ever use the word correlation when you're talking about an association between two categorical variables. Lots of categorical variables are associated. For instance, political party and opinion on same-sex marriage. Those things are associated. Democrats tend to be more in favor of same-sex marriage than Republicans are. That's an association. It's a relationship, but it's not a correlation. Correlation does not apply to categorical variables, only to quantitative variables, only to linear associations between quantitative variables. So whenever you're talking about categorical variables, if you use the word correlation in the same vicinity, you're making a big mistake, and on your AP exam, you'll probably lose points automatically just for saying that. Something definitely to avoid. Okay. Thirdly, R is not resistant to outliers or influential points. That's always worth repeating. Not resistant. Okay, so when you have outliers or influential points, sometimes it's a good idea to calculate R with them and without them and see if they make much of a difference. Okay, number 4, no matter how strong the correlation you have between two quantitative variables, that never implies that one variable causes the behavior of the other. Correlation does not imply causation. Correlation does not imply causation. It's worth repeating. People make this logical mistake all the time. So correlation has pitfalls. You have to be very careful about how you use the word. I would only use the word when I was talking about R specifically, and that would avoid a lot of these potential problems. But remember, never use the word in the context of categorical variables, and never believe that correlation implies causation. It never does.